You know, for almost a century now, humanity has been locked in an invisible war. It's the silent, high-stakes arms race against an enemy that outnumbers us by trillions to one. In this explainer, we are diving deep into that epic conflict, our battle against microbes.
And our story kicks off like so many great scientific breakthroughs with a total accident. It's 1928, and a scientist named Alexander Fleming gets back from vacation, only to find that a stray mold spore had contaminated one of his petri dishes. And he noticed something incredible. Everywhere that mold grew, the bacteria around it just died. He had stumbled onto penicillium, and just like that, we had our very first antibiotic.
Okay, so before we get any deeper, we gotta get our terms straight. The biggest, broadest category for these weapons is antimicrobial agent. This is really the umbrella term for any substance that goes after microbes, whether it's bacteria, viruses, or even fungi.
But an antibiotic? That's way more specific. It's a natural product like Fleming's penicillin that's laser-focused on targeting bacteria. So think of it this way, all antibiotics are antimicrobials, but not every antimicrobial is an antibiotic. That's a really key difference to keep in mind.
All right, so we've got our first weapon. Now we need a plan, right? A strategy. This brings us to the antimicrobial playbook and all the different tactics we use to fight this invisible enemy.
First up, you have to choose your approach. Are you going in with a shotgun or a sniper rifle? A broad-spectrum drug is the shotgun. It takes out a whole wide range of different bacteria. It's super useful when you're not exactly sure what you're fighting. A narrow-spectrum drug, on the other hand, is the sniper. It's incredibly effective, but only against a very specific, limited group of pathogens.
Okay, next question. What's the mission? Total annihilation or just containment? A cytal agent, like bactericidal, well, that's a lethal strike. It just kills the pathogen straight up. A static agent is a bit different. It just stops the pathogen from multiplying. It basically puts the enemy on pause, which gives your own immune system a chance to swoop in and clean up the mess.
So how do they do that? Well, they've basically got four main lines of attack. It's kind of like sabotaging an enemy factory. You can break down their defenses by messing with their cell wall. You can jam up their production lines by stopping protein synthesis. You could cut off their power supply by blocking metabolic pathways, or you could even scramble their blueprints by inhibiting nucleic acid synthesis.
But all of this, all of it, hangs on one golden rule: selective toxicity. See, the absolute genius of these drugs is that they act like targeted assassins. They go after things that the microbes have, but our own cells don't, like a bacterial cell wall. The ultimate goal here is to wipe out the invader while doing as little collateral damage to us, the host, as possible.
Okay, so knowing how these drugs work is one thing, but that's only half the battle. The other half, which is just as important, is figuring out exactly how much to use. This is a super delicate balancing act. It's the science of finding just enough.
And it's all about this balance between two really important numbers. The therapeutic dose is the amount you actually need for the drug to work and treat the infection. But then there's the toxic dose. That's the level where that same drug starts to become harmful to you. The sweet spot, of course, is right in between those two. So how do we measure that safety margin? Well, scientists use something called the therapeutic index. It's actually a pretty simple ratio. You take the toxic dose and divide it by the therapeutic dose. The bigger that final number is, the wider the safety margin and the safer the drug is to use. A small number means you're walking a really fine line.
Now, to nail down the effective dose, labs are looking for something called the minimal inhibitory concentration. We just call it the MIC, and it's exactly what it sounds like. The absolute lowest amount of a drug needed to stop that pathogen from growing in the lab. It's the baseline for effectiveness.
So, that's the goal, right? Find the MIC. But how do scientists in a lab actually find that magic number? Well, they've got some pretty clever and surprisingly visual ways to figure it out.
Okay, check this out. This is a classic dilution test. Each one of those rows is a different antibiotic, and the concentration gets lower and lower as you move from left to right. Then they add bacteria to all the wells. See how the wells go from cloudy to clear? The very first clear well tells you the exact concentration that stopped the bacteria from growing. That's your MIC.
Here's another super common one. It's called a disc diffusion test. You start with a petri dish that's completely covered in bacteria. Then you place these little paper discs, each soaked in a different antibiotic, right on top. If the bacteria are susceptible, you get these clear halos, these zones of inhibition. It's simple. The bigger that clear circle, the more the bacteria hate that antibiotic.
And then you've got a more advanced version, the E-test. This thing is pretty slick. It uses a strip that has a gradient of the antibiotic on it, going from a really high concentration down to a low one. This creates a kind of teardrop shape, and you can read the exact MIC value right there on the strip where the clear zone meets the numbers. Pretty cool, huh?
So we developed all these incredible drugs. We figured out how to dose them perfectly. We really thought we had the upper hand, right? But in any arms race, you have to expect the other side to fight back. And they did. This is how we got the rise of the so-called superbugs.
And here's the thing that might just blow your mind. This isn't some new, modern problem. Almost immediately after we started using penicillin, some bacteria were already figuring out how to beat it. The resistance began at the moment the war did.
And believe me, over the decades, they've evolved a whole arsenal of ways to fight back. Just look at how sophisticated their defenses are. For example, they can create enzymes that just chew up the antibiotic before it can do anything. They can change the drug's target on their own cell. Or they can even use these tiny little pumps to literally spit the drug right back out.
So their playbook, their defenses, they basically fall into a few key categories. They can modify the drug's target. It's like changing the lock so our key doesn't work anymore. They can use enzymes to just neutralize the drug. They can pump the drug out as fast as it gets in. Or they can just find a whole new way to do whatever the drug was trying to stop them from doing. Now this resistance, it comes in a few different flavors. Some of it is intrinsic, meaning a bacterium is just naturally immune. What's more concerning is acquired resistance, where they actually evolve a new defense through a change in their genes. And here's the scary part. They can actually share these genetic blueprints for resistance with other bacteria, spreading it like wildfire. And then you have persisters, bacteria that just play dead and ignore the drug until the coast is clear.
Okay, so this is obviously a huge threat to modern medicine. So what's our move? How are we, today, adapting our strategy to try and win this ongoing arms race? What's our modern counterattack?
Our modern counterattack is all built on a few really critical rules. First, we hit the infection hard with a high concentration of the drug. Second, and you've probably heard this one, and it is so important, you have to finish the entire prescription to make sure no tougher bacteria are left behind. Third, we can use a combination of drugs to attack from multiple angles at once. And fourth, and maybe the most important rule of all, we have to use these precious drugs only when it's absolutely necessary.
And that leaves us with one final, really big question. The enemy in this war is relentless. It's constantly changing, constantly adapting, constantly evolving. The question we really have to ask ourselves is we? Is our science, are our strategies, and our habits evolving fast enough to stay one step ahead?